Okay, welcome to Chapter 7, Virtualization. This chapter is going to talk a lot about virtualization, and the one thing I want us to do is to not really think about it as necessarily a product or something like a VMware or Parallels or VirtualBox or any of the products that are out there. I think those are more the mainstream things that people think about today and when we think about virtualization, but I want us to think about it in a more global scale and to keep in mind that virtualization's been around for 40 years. We've had the same kind of thoughts around technology in mainframes, it's the old IBM 370 days. And really when we think about virtualization, what I want us to think about is how can we compute in a different way instead of just having one operating system on one architecture on one computer. So if you think of VMware or Parallels or any of the other things that are out there, they achieve running different operating systems on a given host operating system, and we'll see the difference between the different types of hypervisors that are out there that kind of run them. But there's many different ways to think about it, and whether it's carving out an environment like we did in the old mainframe days, or if it's a way to think about running, more than one operating systems on a specific machine, that we'll see is one of the types, all the way to, and what we'll talk about at the end, which isn't really in the book, but I think is an important one to talk about, actually running different forms of maybe just code, or maybe just things like different spaces. So what you guys did in Lab 1 around the clone command is actually Linux namespaces, and is another form of virtualization. You'll see that popularized out in industry as Docker or anything around microservices, which Docker can turn into Swarm, that can turn into Google has Kubernetes and various other platforms around that, which, again, we'll talk about at the end. But really what the way I want you to think about it is to break it down to fundamentally running whether it's a process or whether it's, just running a piece of code, but how are we running things in quote-unquote their own space for what is needed. So a lot of what we're going to talk about today is a little more generalized into, the standard, VMwares and hypervisors and things like that. But I want us to draw a little bit deeper into thinking about virtualization in a larger capacity. So when we think about this, a hypervisor, so a hypervisor is a computer that could run either directly as a operating system that only supports guest operating systems, or, as you've seen me do on my machine many times, an operating system that's running that has, let's say, an application that runs and emulates another computer, where all it's really doing is it's saying, oh, okay, well, I'm going to carve out, 2 gigs of RAM and I'm going to give it to you. So from an OS perspective, you've kind of taken those 2 gigs of RAM and you've given it to this process, which is a hypervisor. And let's just take Parallels or VMware as an example. These now start to wall off the two things, but it's interesting how they wall them off, because there's going to be things that are somewhat shared, like a network card is shared. But as you'd see, it kind of breaks them apart, and that's what you saw in Clone when you do new net. It actually creates a brand new quote-unquote fake network card and gives it a different IP address, and lo and behold, those are completely two different architectures, but they're still riding on that one physical card. We've brushed maybe a little on this up till now, but there's this whole concept of software-defined, and so the common software-defined is software-defined networking, SDN. And we'll talk about OpenStack at the end, which is a brilliant kind of container and orchestrator for that. But that's just one example. So we think that when we define virtualization, from a hypervisor perspective, you need to break things apart. So that's at number one, safety. So how do you make sure that when you carve those 2 gigs of RAM out, that the other guest operating systems or even the host operating system, how do you make sure that it doesn't have access? So how do you break those two apart? And that's exactly what you did with Linux namespaces and the clone command, although it wasn't the easiest thing to understand and kind of follow, that's kind of what's happening there. Fidelity, so how do you make sure that it looks and feels exactly the same? And so if you've ever seen VMware or Parallels, any of those hypervisors running, you'll see that there's usually a toolbox that comes with. And this toolbox is the ability to, both kind of make everything seem the same, but also it gives you some interesting tools, like I can kind of cross-mount my hard drives, so that way, even though I am technically on, one hard drive that has multiple logical partitions, I can actually share between them, and I can mount between them, and I can actually see things from either side. And so that's kind of that idea of fidelity. And then, efficiency. What's the point of creating all these new guest operating systems doing things if they're either sitting idly by, or one of them could consume all the CPU? So you can actually carve up many of the attributes around CPU, disk, define different network cards, define things that really support the operating system in different ways. So, aside from kind of these three things, these are really the hypervisor requirements. But I think if you think of microservices, which is a newer kind of topic, and how we define microservices, they run a little different, and they need to be separated for different reasons. I'll talk about it a little bit later, but one of the concepts around microservices is this whole concept of code monkey, which is basically software that goes and destroys your code. So different way to think about it. Normally we build things and we try to test it and we make sure that nothing could ever fail. But microservices are really defined in a way to say, well, I'm going to write my code, and if it dies anywhere along the way, I don't want to necessarily do a rollback. I don't want to, get into that whole, logging and commit rollback kind of concept. But I might want to say, if that microservice dies and it only ran for a nanosecond, let's fire up another one and just get the work done. So different forms of virtualization require different levels of these, but as you see when you get into microservices, that efficiency thing means something a little bit different. So here's the common type 1, type 2. And so, the idea would be around a type 1 hypervisor would be something more like Citrix, or VMware has NSX, different ways of creating these, where it's a very, very lightweight operating system. So it doesn't have all the necessary components to make a full operating system work, because its only job is really to fire up the guests. So that's the type 1. Type 2 is what you've seen me do with Parallels on my machine quite often, where I can flip between my machine and a Linux machine, or any of the other hosts that I want to spin up, knowing that its job is really to be its own operating system, and then firing up guests at will. So this would be my Mac host process over here on the right, and then my guest being, Linux or CentOS or Ubuntu, or maybe all of them run at the same time. And I've got some, experimental and other ones like Elementary and Haiku. So it doesn't really matter. But the interesting things that both of these do is they kind of abstract away the hardware, and they kind of create generic versions of things. So when Linux boots up, I might have a very specific network card in my Mac, but what the actual hypervisor is going to do is create a generic layer to say, okay, well, maybe you just have a plain, boring SMC network card, or you've got a whatever, and it abstracts all those things apart from each other. So that's why you see things like, generic USB interfaces. You see, hard drives and mounting as you would natively to your given device, even though I might have a completely different architecture. I might be running different versions of 32 or 64-bit. So again, I need those things, normalized as they actually kind of go through the operating system to the actual hardware. I'm sorry, I said NSX. I meant ESX. NSX is the SDN version that VMware has. So looking at the two, you might see that VMware does have two different flavors. So VMware Workstation would be the thing you would put on your laptop or home machine, and then fire up more guest OSs, where ESX's only job is to be loaded as an operating system, and then through vSphere or other forms of software like we have here, that actually manages creating guest operating systems and defines on how they're running. We have Zen and Q. I'm trying to think. There's a couple other ones. They're fairly common. We'll see them kind of coming up here. Wine, I don't know. Wine is a different thing. It's a Windows emulator, which isn't necessarily a full hypervisor per se. Really, it's more of an emulator that lets you kind of run Windows programs through it, but not necessarily, being able to quote unquote dive into a full operating system. Now, you got to step back a second here and think about the fact that when we're talking about virtualization, when we talk about type 1 and 2 hypervisors, one of the things you're doing is you're actually splitting resources. So you're actually saying that, as an example right now, I've got a CentOS machine running, and it might be taking, out of my 16 gigs of RAM, maybe I give it 8. That means my main OS still only has 8. I can't kind of slush back and forth. That isn't really that efficient because maybe I fired up 2 more guest operating systems, and each of those I gave another 8. Now I can oversubscribe, I can kind of use that, but if they all started doing stuff at the same time, I would start thrashing, I would start swapping data in and out of memory, and really isn't that valuable. So the standard of taking necessarily, of course my laptop, I'm doing it for academic purposes, not just the U, but just to show people or look at things. So I'm usually in one or the other. So that's usually not a big deal. If I'm going to put this on the server, of course I'm going to use a type 1, and I'm going to get into the fact that that operating system that's running, I assume, is going to be doing work. And they're all going to be doing work at the same time. So in doing that, as I look at this example of a type 1 here, where I've got the hypervisor running and the user mode is again broken into its own different, as you see, virtual kernel and virtual user modes. How do I manage and support the fact that I could have 10 interrupts at the same time for the same exact hard drive running through there? So the OS does need to be, the type 1 OS like ESX has to be smart enough to know how to share that load and know that, we're not going to give priority, we're not going to give one OS preference over the other, unless we really want to do that for some reason, which is an option. But, really we're after trying to make sure that we've got that fairness again, where as things are running, they all seem like they're all running, perfectly real time, nothing's getting in the way. We're making sure that we're, executing and building across the board in the right ways, and at the end of the day, we do have full function. But it's a little inefficient in the carving up kind of modes where you're kind of dedicating things, because operating systems don't really run quote unquote all the time. Even web servers, even file servers, things that seemingly are doing a lot of I/O, whether it's through sockets or disk. They're still not always quote unquote running. They're mostly in sleeping or waiting modes. So I think we get a little artificial efficiency out of some of it just on what's happening versus them kind of running as they need. This is where we kind of step back and said, okay, we need a better way to do this, and that's how the advent of microservices actually came. And the concept of being able to run, a little bit more of, kind of what you need when you need to. In industry, we use the word elastic a lot. And elastic is really just to say that, at a certain amount of time, I only need X amount of resource. I need 2.8 meg of RAM or 2.8 gig of RAM. And maybe the total sum for any given OS would be a certain amount. The problem is that with the hypervisors in type 1 and type 2, we don't have the luxury of making those elastic because an operating system can't deal with things being that way. I can't give and take large chunks of memory like that. An operating system just isn't designed to do that. They're designed to have very static things. They have things that they think are dedicated to them. So at the end of the day, even in a type 1, but more importantly a type 2, we would have to look at this stuff that we're using, the resources we're using, and we have to figure out how to divvy them up. And that's technically why we really can't get to that elastic nature, which is, why we've kind of pushed through this whole SDN into, fully elastic things. Now, there are things that don't, as I was saying before, that really don't or can't understand what virtualization is. I can virtualize things, like I can make more than one network card. I can make an operating system believe that it's on, dedicated RAM, not knowing that there is any other RAM. I can deal with I/O in certain ways, of a virtual hard drive in its own kind of chopped up space. I can even get a little fancy with making hard drives somewhat elastic, where I can grow and shrink them because they're logical volumes. They're not the actual physical drive. But what do we do when a guest operating system, assumes that it has full control, there is nobody else, and it goes and, tries to do something that is really not virtualizable? And that's really where the hypervisor has to come in and, kind of define things in how they run in different ways. And so some of the tools that come in, like I was talking about those toolboxes, some of them are kind of inherently built to help with this. And you can actually see the performance differences between different type 2 hypervisors with the toolboxes on versus them off, in wait times and, how I/O is actually completed. Now, how are these kernels actually defined? So when we think about Linux and, is it, microkernel, monolithic, which it's monolithic, how did Apple deal with different, like Mach-O and that over the years, being a little more microkernel based? How do those map? And how do we have to make these things actually treat each other the same way? Again, in type 1 versus type 2, type 2, you're kind of stuck with the native host OS and how those things get mapped, which is a little less efficient, versus kind of thinking about how things could actually flow through a different type. So Linux being monolithic, going through a microkernel, is more paravirtualization. It's more of a interpreted, I guess would be a better way to look at it, much like we've got, native C code talks directly to the operating system through library calls and everything's hunky-dory, but then if we want to use Perl, which is interpreted, we have to go through that interpreter to get things done. So we can kind of take these through and we can know that we're dealing with, virtualization directly to bare metal, which is A. B is just a version of, VMware through a library call. And so obviously the VMware library is going to be the thing that deals with normalization. But again, it's going to go down and it's going to talk to the VMware software. And so if this is type 1, you'd be talking ESX, which its only job is to, be there to support the guest OSs. But if it's type 2, it might be that I'm doing other things and that OS needs to wait. But it is an interesting thing to think about that, let's say you have a process that is, your lab 2, and there's another process that's dealing with find command in a shell, and then there's the actual VMware or Parallels hypervisor. How do you break that apart and give the right priority to different things? Is it luck of the draw that nothing else is running? Or is it that your find command could actually slow down your VMware because it's vying for the not the exact resources, but the same kind of resources at the same time? And how does that kind of break down? And Zen or any of the other ones kind of done the same. So it's interesting to think about how these operating systems utilize the guest operating system, and again, that difference between type 1 and type 2. Now, we've talked about this 3 weeks ago on memory and virtual memory and how do we get access to things. Kind keep in mind it's not going to be any different here. It's just the fact that now we're taking this whole, let's just say, massive process of VMware or Parallels running on my machine. And when I need memory for that guest Linux, CentOS or Ubuntu that I'm running, it's no different than any other process calling malloc, and I need the space. And even though the native OS, we'll just say Ubuntu, is running as a guest, might call malloc, it's going to go back to its operating system. It's going to ask for memory, but it's not going to necessarily be getting it from the kernel it expects it to. It still has to go down and ask the question of, Parallels, as an example, a process running, which then gets down into, okay, well, how do we get that? How do we get that actual memory? How do we convert, from the virtual to physical memory, and how do we deal with, the whole concept of pages and page faults and everything we talked about before? And, again, we think about this as, putting Parallels or VMware player or workstation into its category of a process, knowing that it is the thing that's actually going to have that actual call, and it's going to have that whole virtual piece to it. So think about if you wrote a program that basically went down and said, okay, I need 2 gigs of memory, and I'm going to, what am I going to do? I'm going to malloc that, or am I just going to carve it up? Do I have, through the operating system, an ability to say that I own that 2 gigs? Or am I just going to go down and say, from a virtual memory standpoint, so not physical, but virtual, I need 2 gigs of memory. The operating system will kick that back. Everything's good to go. You have your 2 gigs. That's yours, virtually. But you never have it physically. So it's that whole concept that we've talked about before where I actually want that memory. I want to go actually use it in that guest OS. And I thought I had it. I said I had it, but I had a page fault. And I had to go down and really pull that stuff out. Today's world is much different than it was 10, 15, especially 20 years ago, or more, where, 4 megabytes of memory was a big deal. Having 8 to 16 in any given architecture, any given platform, pretty commonplace, pretty cheap these days, and you're probably not going to run out. But what if I was to go virtualize, 4 OSs on 4 megs of memory? We're going to have a lot of problems. So I think we can afford the luxury of the fact that we're not needing to, go beyond page faults to swap and actually kick things out. But I would tell you that I know, if I was to look at my given machine here, let's see, so you can see this. Pull this into view so you can see it. So again, here I'm looking at top, and everybody's vying for everything. And I do know that because Parallels is on, I'm just verifying that's on. Yep, I see it there. So Parallels is running. I do have, let's see here, let's CPU. So I can see, what's getting kicked off, Windows Server, Launcher, blah, blah, blah. I saw all this stuff in here. But if I look at the top, I can see, 462 total processes, 2 running. But I look at my physical here, and I can see that I'm pretty well, at that 14 gigs used, with a little over a gig, 1.67 unused. But if I was to go down to Parallels here, and let's go ahead and quit this. And okay, I gotta quit one more thing. I'm not seeing it go away here. Yeah, I was assuming that was going to drop. Let me fire it up here. I might not have had a guest OS running. Yeah, let's go fire up. So I'm going to fire up this Ubuntu image here. And I'm just going to minimize this to get out of the way. And now I'm up to my max. So you can see that and I think I've only got it pulling 2 gigs out to that. But now if I was to go to that guest OS and basically kill it, we saw that go back down to that 14. So I'm kind of up in my max there. I'll have to look at why I've got that all set. But you got to put all this into perspective, kind of what's doing what. Now, is it that if I fire this up one more time and I look at my top, so I'm at my 14. I'm going to start this. You see that jump back up to the 16. But look at my virtual. So I've got 2.3 terabytes. And if I go ahead and end this again, we're down to 2.2-ish terabytes. So in how I've done memory allocation, in how I've kind of utilized how this memory is being created, really what I've been doing is kind of more playing in the virtual space. And yes, I did need to allocate a certain amount. I did go to the actual kernel in the guest OS and the type 2 hypervisor and say, hey, I don't think I've got 2 or 4 gigs kind of nailed up. I do need that space, but it's going to allocate it more in that virtual space. And then again, how these different guests actually go get these are kind of somewhat analogous to a process running, just knowing that Parallels is now the actual process that's running on my host. Now, cloud is one of the most, it's kind of like AI these days, one of the most overused terms in our space, and I would be really careful to kind of just use this as something that you're trying to define something with, because cloud, it can mean anything from somebody else's data center to how you pay for it to how it's consumed. I'm going to use more of that elastic concept, because most of what we're going to try to deal with in a cloud space is a resource that we use and we pay for only when we need it. So hypervisors aren't a good example of that, because and CERN has this poster that you can see too, with a picture of a kitty cat on the top and cows on the bottom. And it basically defines down that, treat your servers or treat your compute resource like animals, not like kitty cats. Don't name it, don't have affinity to it. Just know that if you don't need it anymore, you kill it, you move on, and when you need more, you ask for more. So that's more of what we call the cloud consumption model, or the cloud elasticity. And that's really where I think the value comes in, and really what we're talking about in virtualization space. So on-demand self-service. Well, if I go on Amazon right now and I want a new server, I just click a button, boom, I get one, good to go. It's not technically, to me, a hypervisor. It's more of that software-defined. I get it spun up, and I get some hardware or a hard drive from somewhere. I get some network card from somewhere, RAM from somewhere, CPU from somewhere. I don't really know or care where it is. Number 2, I wouldn't worry about. Number 3, but it's really number 4 that's kind of the key. As I have that instance, there's certain things I can do, like I can turn services up, turn them down. I could increase RAM, decrease RAM. If I do that on the type 2, I have to shut it off before I can do that, because a native operating system can't handle and deal with certain things changing on the fly. So, cloud, again, a little bit overused of a term. One of the things that became quite interesting, especially in the x86 architecture, is how it was never meant to be virtualized. And so the software that would write on the top had to do a lot of the work that we couldn't just do native in the architecture in the OS. We had to think a lot more about, what would it look like to have, memory carved up like that? What would it mean to share a common bus to CPU or I/O and caches and all the other stuff that's kind of in the mix in a x86 versus other forms of architectures. And how do we create tenancy? Let's call it, instead of isolation. How do we create the fact that all these guest OSs should be treated fairly and they should consume it how they want to? Again, I just go back to kind of natural selection and how the world really works. If I'm in a type 2 environment, I'm on my laptop, and I'm probably not in both operating systems at the same time, right? I got to move back and forth. Well, if I'm in my Ubuntu guest, and I'm clicking, and I'm writing code, and I'm running things, and I'm looking at web pages, well, that means the host OS, my Mac, isn't doing anything. So there's really nothing to worry about. And if I go back to my host OS, I'm not in my virtualized guest or guests, so nothing's happening there either. So I'm affording myself, even though I'm kind of maxing out on all my resources, this ability for things to be fair and to be treated really well, because I as a human interfacing with it, I'm only doing one thing at a time. When you go to a type 1, you have to think a little bit more about what we're actually doing, because that server is getting chopped up into, let's say, in a Dodeca 12-core machine, I might have 6 different machines all running 1 to 2 CPUs, and as those OSs are running, it's kind of assumed that they're all working at the same time. But again, they're operating systems. Their job in life is to do a few things, and if they're servers, it's not a human sitting on that machine running commands and using a mouse and a GUI interface. They're usually there to do one of a few things. They're going to be a file server. They're going to be a network router. They're going to be a web server. Any form of these different servers. And again, if nobody's going to those sites, if nobody's transferring files, nobody's doing that I/O, then it's not doing anything. So we sometimes afford that way, but the problem that we've got in the type 1 in that scenario is that same problem that we had with file systems, memory allocation, and it's in fragmentation. It's not in external fragmentation because there are no spaces between guests running, but it's at internal fragmentation, and it's not more space, but it's more resource. So I could have one machine that's just getting throttled, and I just didn't give it enough memory, I didn't give it enough CPU, I didn't give it enough resource of whatever kind. And it could be that, out of those 6, one's getting thrashed and it's falling apart and it isn't doing anything, and the other 5 are just sitting there idly by doing nothing. And it's not that efficient, it doesn't really work that well, but when we think of that kind of tenancy model, that's really all we have in the the type 1, 2 hypervisors. So, x86 was never designed to be virtualizable. Back in a little bit of a history lesson, so this was created, at least I started running into 386s in the late 80s, early 90s maybe. So we went from, there was 286s. That was, prior to me really getting involved in a lot of it. But 386 was a start. Then they went to 486 and 586, and that kind of got us through the 90s. And then Pentium and all the things that came after that. But the whole idea, which is still kind of the mainstay of what general computing has out there for us, is this architecture. And yes, we flipped from 32 to 64-bit, and that was about it. In the past couple decades, but it was never meant to be virtualizable. It is very complex because we, over the years, had tried to create things to run faster, but based on the problem at hand, which was, how fast we can make things run faster. So there was a time where we actually cared about how fast RAM was, and we would look at buying different kinds of RAM based on different kinds of speeds. We don't look at that anymore. CPUs were a big deal. You know, when we went from a 1.6, megahertz or, into gigahertz, everything kind of plateaued and it wasn't that big of a deal. I/O was a big deal. It still always is, but, I/O from a hard drive perspective, knowing that that's one of the slowest things you can do in an OS, was a little bit daunting, and we went from, certain architectures like IDE to SCSI was kind of the mainstay, and SCSI afforded us a lot of cool things. Resiliency and redundancy and high availability was the major factor, but with striping we could actually make I/O happen faster because we could have parts of files on many drives at the same time, and we could ask 5 drives for parts of a file instead of 1 drive for 5 chunks of a file. So anyway, that made it extremely complex, and then the whole buses, the ISA to PCI to PCIe, and how that all interfaced to different things, what was actually stitched on board, and the whole thing just very complicated, and a lot of components that kind of went back and forth, and then also how the operating systems managed a lot of that through device drivers and through kind of native machine code made it a little more, maybe a lot more complicated to virtualize that whole space. But again, it was really intended to be a general purpose OS that supported everything from various versions of Unix to Windows to now Mac, which is really BSD Unix, so maybe back to that. Every kind of flavor of Linux. But if you went and looked at some of the other architectures out there like Spark or MIPS or RISC, all the other ones, even some of the Unixes had different flavors. Spark, as an example. They were a little more simplistic in how their architecture and model was built, but just to know that x86 was the most complex because it has just so much going on, because it was grown up over generation to be more user friendly. So in this, we have to think about how do we get to a model where in this architecture we can leverage, let's say the physical components in the architecture, but again in that fair way, knowing that there's certain things like MMUs as hardware that require something to make a decision, which maybe we didn't have to make before, because if it was a single operating system and a single resource, the kernel owned it. There's nothing to think about. Now we've technically got 2 or more kernels, kind of all vying for the same physical thing. So again, we can't emulate an MMU as an example. If we did, we would slow that OS down quite a bit, and the OS would have to have some piece of code in it to say, oh, if you're virtualized, use this fake piece of software in the kernel versus this physical thing, and the physical things are always going to be faster than virtual because the software-based thing is going to run it out of RAM, and that RAM's going to be slower than some of these other things. So, how do we gauge and manage that? And in a lot of that, there's whether it's, we didn't talk about the kind of this whole concept of binary translation, but how do we think about these multiple kernels running at the same time? So in the virtual machine itself, let's say the guest in number 1 is running a kernel mode. Does it have the power and capability to turn on and off interrupts? More importantly, turn them off, because now the host can't do the same thing. So if any of these are true, then you have to think about this binary translation, because you have to ask who really does have control and access to it. So if the VM's in kernel mode, meaning it's kind of doing something at a level that the OS expects that it's the only thing that owns it, now, number 1, by definition means that because I have 2 or more things in kernel mode, potentially, and I know that if I've got my virtual machine, my guest, in that, there's probably a good chance that my host is going to do that as well. I can't deal with the fact that there's 2 in there, so I have to use this kind of binary translation to figure out who really has it and who doesn't. And that was just, kind of a bigger thing in virtualizing something that wasn't built to be virtualized. Now, VMware, I think, is one of the oldest in the space of doing virtualization on x86. Again, like I said, in the 70s, we were doing it on IBM 370 mainframes. Obviously much different. Linux has created namespace, which is more software, kind of up the chain a little bit, built for microservices, not built for putting more OSs on. So we don't have that problem there, and we don't have that problem down in the mainframe because it's just completely different architectures, completely different ways of thinking about it. But, if we think about, this conflict and how it was dealt with, back in the day, we think about this kind of concept of, being multiplexed where if I have a single x86 CPU where I have to share that amongst 2 or more kernels, we'll just call it, we have to figure out how to make choices. And in what we can do, kind of, and this was kind of the first initial ways of getting this done, is, having the host OS figure that out. And even in multiprocessor, if we have 2 or more, we can carve things apart. But if you think about, I don't know if we've talked about this much, but the difference between symmetric and asymmetric processing through CPU, most everything is done symmetric, which means the host OS or the main OS has control of all of them and is the one that kind of dolls out who goes to what. But if in a virtual space we actually carve those up and we say, okay, well, you get these 2, somebody else gets the other 2 out of a quad core, then we can say to ourselves that we've got those things split up, but we still need somebody to control it. So we still have to have something doing what's really called long-term scheduling, which is job scheduling, down to short-term scheduling, which is CPU scheduling. And even from a RAM perspective, are we actually calling malloc from the guest OS, knowing that that's also going to call malloc from the host OS? And what does that mean? Do I actually get it? Is it virtualized? Are we going to get into swapping and paging? And so all that had to be thought through. But again, this is back, almost 20 years ago, and a lot of advances have come. But I would tell you that the wave of the industry is to even get away from virtualization because we've kind of pushed the limits as far as we can. And the fact that the OSs are not meant to be elastic, and an OS isn't meant to be elastic, just by its nature. And there's no reason to go start creating a new version of Linux that would be, just because a lot of the paradigms and a lot of the algorithms and problems that we've solved don't really make sense if there's more than one thing controlling or having access to things. So, again, back in the day, this is kind of what we started with. This is another way that we kind of said, okay, let's take, and regardless of what you really have, so as an example, on this PCI bus back in 2000, there was 4 physical IDE disks, 7 SCSI disks as an example, and what really happens is, it was that virtualized partitions were created. Then we actually started to create volumes, and volumes could be things that map across many devices, different kinds of devices, because it's just logical mapping. It's just saying, okay, well, this block's here, that block's there, you go to this memory for this, you go to that memory for that. What it would look like from a guest OS, and I think they just use kind of this generic driver concept, but your generic hard drive, your generic, so it could be the most fancy SCSI fiber channel, NAS device you've ever seen. It might show up as a generic IDE hard drive because that doesn't change anything in its physical characteristics or its speed or anything about it. It's just known that when that device is asked to do I/O, it answers the question from an abstracted standpoint. Yes, I can open. Yes, I can close. No, I can't read. No, I can't write. Or I can read and write. None of that really matters. And the rest of these kind of follow through is kind of what the defaults were there. So I'm going to end this one and start number 2.